Hello, chemists. We're going to take a look at something called the conservation of mass and the law of constant composition. Now, conservation of mass is the idea that mass cannot be created or destroyed in chemical reactions. And the key on this is chemical reactions. You may have seen this equation here, E equals mc squared. And in this equation, we have the speed of light, we have mass, and we have energy. And with this equation, it tells us that if you take a certain amount of mass times the speed of light squared, you get an amazing amount of energy. Now, this is more of a physics thing. In chemistry, we're not going to be creating mass or energy back and forth like that. What we're going to be doing is taking a look at chemical equations. Now, conservation of mass was proposed by a French person named Antoine Lavoisier. And the basic idea is that matter cannot be created or destroyed in chemical reactions. And so an example of this would be as if we take, say, sodium and chlorine and react them together. So sodium and chlorine react together and give us sodium chloride. Now, the elemental symbols are not terribly important at this point, but let's just take a look at the masses. So, for example, if we had 11.5 grams of sodium, and this completely reacted with 17.7 grams of chlorine, this would give us some amount of product. Now, if all of this and all of this are used up to give us our product, we would end up with 29.2 grams of sodium chloride. And if we add these two numbers together, they should add up to this number here. And that's because matter cannot be created or destroyed. Now, if for some reason we reacted this and we reacted that together and we got less than this number or more than this number, well, then something strange is going on in this chemical reaction. All right, let's take a look at another problem using the conservation of mass. In this chemical equation here, I've got methane, which is natural gas, reacts with oxygen and gives us carbon dioxide and water. This is a combustion reaction. Now, remember, whatever we have as reactants must equal the mass of our products over here. So for example here, if I have 6.4 grams of methane, and it completely reacts with 25.6 grams of oxygen, like this, and let's just say it produces 17.6 grams of carbon dioxide, well then how much water here is produced? Well, we can think of this as like a mathematical equation. 6.4 plus 25.6 equals 17.6 plus some amount. And we know that this side here has to equal this side over here because matter cannot be created or destroyed in chemical reactions. So if I add these two together and I subtract 17.6, that should give me what's left over here in water. And in this case, it's 14.4 grams of water. Now, taking a look at constant composition. The basic idea of constant composition is that atoms are arranged in compounds in the same proportions. Now, this was proposed by Joseph Proust, another French person. And an example of this would be going back to sodium and chlorine. So if we have sodium and chlorine, and we look at the proportion between these two, sodium atoms to chlorine atoms in sodium chloride. Now, in in this ratio here, the sodium to chlorine here, if we have, say, 11.5 grams of sodium reacts with 17.7 grams of chlorine, this is a ratio. And this ratio turns out to just be 11.5 divided by 17.7, 0.65, not grams, 0.65 is just our proportion between these two. Now sometimes we get nice even numbers, sometimes we don't, and that doesn't really matter here. But the ratio here is 0.65. Now if we were to take a look at two other masses combining here between sodium and chlorine, another example would be 23 grams of sodium would completely react with 35.5 grams of chlorine. And if we take 23 divided by 35.5, we'd end up with the same ratio. And so the idea is that when we have compounds, the ratio of the elements in the compounds are always the same if it's the same compound. Water, we might remember water is H2O. It's always H2O. It's always two hydrogens and one oxygen. It's always in that ratio. And if it isn't, well, then it's not water.